So we now look at dividing polynomials and then using this method to find the roots of polynomials. So recall that if we divide an integer by another integer, we get a quotient and possibly a remainder. In other words, we can write any integer in the form z equals dq plus r, where d is called the divisor, q is the quotient, and r is the remainder. Also, r is 0, or any number less than d. This is known as the division algorithm for integers. And as it turns out, there's also a division algorithm for polynomials. And here it is. Given any polynomial f of x and non-zero polynomial d of x, where the degree of d of x is less than or equal to the degree of f of x, there exist unique polynomials q of x and r of x, such that f of x is equal to d of x times q of x plus r of x, where the degree of r of x is less than the degree of d of x, or r of x is 0. F of x is called the dividend, d of x is called the divisor, q of x is called the quotient, and r of x is called the remainder. Another way of writing the division algorithm is f of x over d of x is equal to q of x plus r of x over d of x. So when we divide two polynomials, there are two ways to go about it. The first is known as polynomial long division, or simply long division. The second method is called synthetic division. Long division works in much the same way as it does for integers, and synthetic division can only be used if the divisor is linear with a unitary leading coefficient. So unitary leading coefficient just simply means that the leading coefficient is 1. So to use polynomial long division, first set up the division problem. Determine the first term of the quotient by dividing the leading term of the dividend by the leading term of the divisor. Multiply the answer by the divisor and write it below the like terms of the dividend. Subtract the bottom polynomial from the top polynomial. Bring down the next terms of the dividend, and repeat steps 2 through 5 until reaching the last term of the dividend. If the remainder is non-zero, express it as a fraction using the divisor as the denominator. And we're going to go ahead and see these steps in action in the next few examples. So first, we will divide 5x squared plus 3x minus 2 by x plus 1. So to set up the division problem, we put the divisor on the outside. We'll put the dividend inside, so 5 squared plus 3x minus 2. So 5x squared divided by x is 5x, so that will be written up here. Now 5x times x is 5x squared. 5x times 1 is plus 5x. Now what we do is we're going to subtract that polynomial. So 5x squared minus 5x squared is 0x squared. 3x minus 5x is negative 2x. And then that negative 2 will carry down. Now it'll be negative 2x divided by x, which is negative 2. So negative 2 times x is negative 2x. Negative 2 times 1 is negative 2. We now subtract the polynomials. Negative 2x minus negative 2x is 0x. Negative 2 minus negative 2 is 0. So we're left with a remainder of 0. So therefore, 5x squared plus 3x minus 2 over x plus 1 is equal to 5x minus 2. Or we could write it as 5x squared plus 3x minus 2 is equal to x plus 1 times 5x minus 2. Either of these two ways of writing it are valid. Now, typically, the convention is if all we're doing is dividing, then we'll write it in this form. However, if we're trying to factor, then we'd write it in this form. So the next problem, sorry about that, 6x cubed plus 11x squared minus 31x plus 15 by 3x minus 2. So again, we want to set up the problem. 3x minus 2 on the outside, 6x cubed plus 11x squared minus 31x plus 15 on the inside. So 6x cubed divided by 3x is 2x squared. So we get 6x cubed minus 4x squared. Subtract it. We'll get 0 plus 15x squared. Now we want to carry down the next terms. So we have minus 31x plus 15. 15x squared divided by 3x is plus 5x. So we have 15x squared minus 10x. And we want to subtract this. 15x squared minus 15x squared, that's 0. And we're left with negative 21x. And then we just count this plus 15. Negative 21x divided by 3x is negative 7x. Negative 7x times negative 2. I'm sorry, it's not x, it's just minus 7. Would be plus 14. We now subtract. We'll be left with 0, and then 15 minus 14 is plus 1. So here we have a remainder of 1. So therefore, 6x cubed plus 11x squared minus 31x plus 15. I'm not going to have enough room. Let me write it further over. 6x cubed plus 11x squared minus 31x plus 15 divided by 3x minus 2 is going to equal 2x squared plus 5x minus 7, and then plus 1 over 3x minus 2. Right, or we could write it as 6x cubed plus 11x squared minus 31x plus 15 is equal 3x minus 2 times 2x squared plus 5x minus 7, and then plus 1. Again, either form would be acceptable. So now we look at the steps for doing synthetic division. First, we write k for the divisor. We write the coefficients of the dividend. We bring the lead coefficient down. Multiply the lead coefficient by k. write the product in the next column, add the terms of the second column, multiply the result by k, write the product in the next column, repeat 5 and 6 for the remaining columns, and then use the bottom numbers to write the quotient. The quotient will have a degree that is 1 less than the dividend. And again, we're going to use the next couple examples to illustrate synthetic division. So we will divide 5x squared minus 3x minus 36 by x minus 3. So remember, using synthetic division, it's of the form x minus k. So this x minus 3, k would be 3. Now we want to write the coefficients of the dividend, so it's 5, negative 3, and negative 36. And by virtue, this term right here will wind up being our remainder. So what we do is we carry down this 5. 5 times 3 is 15. Now add them, so minus 3 is 12. Times 3 is 36. Minus 36 is 0. Like I said, that 0 is our remainder. So therefore, 5x squared minus 3x minus 36 divided by x minus 3 is equal to 5x plus 12. And there's no remainder. Now let's look at 4x cubed plus 10x squared minus 6x minus 20 divided by x plus 2. So this gives us a k of negative 2. So the coefficients, 4, 10, negative 6, and negative 20. And again, this term right here will wind up being the remainder. Carry down the 4, multiply by negative 2 is negative 8. Now add these two terms, we get positive 2. Times negative 2 is negative 4. Add these two terms gives us negative 10. Times negative 2 is 20. Add those two terms gives us 0. Therefore, 4x cubed plus 10x squared minus 6x minus 20 divided by x plus 2 is equal to 4x squared plus 2x minus 10. So that is how we divide polynomials. We will now begin looking at how we can use this to find the zeros of a polynomial, or the roots of a polynomial. So the first thing we study is called the remainder theorem. And the remainder theorem states, suppose that in the division algorithm, d of x is equal to x minus k for some constant k. Well, if that's the case, then f of x would be x minus k times q of x, some remainder r. Well, f of x, or I'm sorry, f of k would then be k minus k times q of k plus r. This is 0 here, so all we're left with is r. So the remainder theorem is, if a polynomial f of x is divided by x minus k, then f of k is equal to r. Let's go ahead and apply it. We will evaluate f of x equals 6x to the 4th minus x cubed minus 15x squared plus 2x minus 7 at 2. So we're going to use the remainder theorem to do this. So we're going to divide this polynomial here by x minus 2. And we're going to do that using synthetic division. So 2 will have 6, negative 1, negative 15, 2, and negative 7. And the idea is we want this term right here. That's the remainder. So carry down the 6. 6 times 2 is 12. Minus 1 is 11. Times 2 is 22. Minus 15 is 7. Times 2 is 14. Plus 2 is 16. Times 2 is 32. Then minus 7 gives us 25. Therefore, f of 2 by the remainder theorem is 25. Next up is the factor theorem, which says let f of x be a polynomial. K is a 0 of f of x if and only if x minus k is a factor of f of x. So to see why this is true, if k is a 0, then f of k is 0. That's the definition of being a 0. So by the remainder theorem, the remainder when f of x is divided by x minus k is 0. So we can write f of x equals x minus k times q of x plus 0, which is x minus k times q of x, some polynomial q of x. This means that x minus k is a factor of f of x. However, if x minus k is a factor of f of x, then there is some polynomial q of x such that f of x is x minus k times q of x. But if we add 0 to it, it doesn't change anything. So we have x minus k times q of x plus 0. So by the remainder theorem, f of k is 0. So this proves the factor theorem. Now again, we're going to apply the factor theorem. We will show that x plus 2 is a factor of x cubed minus 6x squared minus x plus 30. Then we will go ahead and find the remaining factors and use these factors to find all the zeros. So remember, to show that x plus 2 is a factor, all we have to do is show that the remainder, when you divide the polynomial by x plus 2, is 0. So we have negative 2, 1, negative 6, negative 1, and 30. Carry down the 1 times negative 2 is negative 2, minus 6 is negative 8, times negative 2 is positive 16, minus 1 is 15, times negative 2 is negative 30, plus 30 is 0. So this means, by the factor theorem, that x plus 2 is a factor of x cubed minus 6x squared minus x plus 30. And so that little proof is complete. Now we want to determine the other factors. Well, x cubed minus 6x squared minus x plus 30 would thus equal x plus 2 times x squared minus 8x plus 15. Now this is a quadratic, and we know how to factor that from algebra. So we want factors of 15 that, when added together, give you 8. Well, 3 and 5 when added give you 8. So we're going to have a 3 5, this final term being plus, means that both of these will take on this minus sign. So the other two factors are x minus 3 and x minus 5. So therefore, the zeros are negative 2, 3, and 5. So now we look at the rational zeros theorem, and this will tell us how we can determine all the possible rational zeros of a polynomial just by looking at it. So we let f of x be a polynomial with integer coefficients. Then every rational zero of f of x is of the form p over q, where p is a factor of the constant term and q is a factor of the leading coefficient. So we will again now see this in action. Given the polynomial 2x to the fourth minus 5x cubed plus x squared minus 4, we wish to determine or list all the possible rational zeros and then determine which of these are actually zeros. So the first thing we want is p. So these are the factors of negative 4. So factors of negative 4 would be plus or minus 1, plus or minus 2, plus or minus 4. The factors of the leading coefficient, plus or minus 1, and plus or minus 2. So all of our possible rational zeros p over q. So we have plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 4 over 1. Then we have plus or minus 1 over 2, plus or minus 2 over 2, which is just 1, plus or minus 4 over 2, which just gives us 2. So here are all of our possible rational zeros. We have 8 of them. Now for the tedious part, to check whether any of these are zeros. So we're going to do this using the factor theorem, or the remainder theorem, right? So to be a zero, the remainder has to be 0 when we do synthetic division. So we'll start with positive 1. We have 2, negative 5. The x squared term is 1. Positive 1. The x term, there is none, so that's 0. And then the constant's negative 4. And remember, it is this last term that we care about. That has to be 0. All right, so carry down the 2. Times 1 is 2, minus 5 is negative 3. Times 1 is negative 3, plus 1 is negative 2. Times 1 is negative 2, plus 0 is negative 2. Times 1 is negative 2, that's negative 6. Uh-oh. That is not 0. So 1 would not be a 0. So I'm going to keep all this set up. We now try negative 1. So again, carry down the 2. Times negative 1 is negative 2. Minus 5 is negative 7. Times negative 1 is 7. Plus 1 is 8. Times negative 1 is minus 8. Plus 0 is minus 8. Times minus 1 is 8. Minus 4 is 4. That is not 0. So negative 1 is also not a 0. So now let's try positive 2. Times 2 is 4, minus 5 is minus 1. Times 2 is negative 2, plus 1 is negative 1. Times 2 is negative 2, plus 0 is negative 2. Times 2 is negative 4, minus 4 is negative 8. That's not a 0. So now let's try negative 2. 2 times negative 2 is negative 4, minus 5 is negative 9, times negative 2 is positive 18, plus 1 is 19, times negative 2 is negative 38, plus 0 is negative 38, times negative 2 is positive 76, minus 4 is positive 72. That's not 0. So now let's try positive 4. 2 times 4 is 8, minus 5 is 3, times 4 is 12, plus 1 is 13, times 4 is 52, plus 0 is 52, times 4 is 208, minus 4 is 204. That's not 0. So now let's try negative 4. 2 times negative 4 is minus 8, minus 5 is negative 13, times negative 4 is 52, plus 1, 53, times negative 4 is negative 211, plus 0 is negative 211, times negative 4 is 848, minus 4 is 844. That's not 0. So now let's try positive a half. So 2 times a half is 1, minus 5 is negative 4, times a half is negative 2, plus 1 is negative 1, times a half is negative a half, plus 0 is negative a half, times a half is negative a quarter, minus 4 is negative 17 quarters. That is not 0. There's now only one left to check. Negative a half. So 2 times negative a half is minus 1, minus 5 is negative 6, times negative a half is 3, plus 1 is 4, times negative a half is negative 2, plus 0 is negative 2, times negative 1 half is positive 1, minus 4 is negative 3. That is not 0. Therefore, none of these are 0. Which means the polynomial doesn't have any rational zeros, which is not a violation, right? Remember that the rational zeros theorem simply says that any rational number of the form p over q could possibly be a 0. Also, it's stating that if a rational number is not of the form of p over q, then it cannot possibly be a 0. So now we want to determine, well, how many positive real zeros do we have and how many negative real zeros do we have? This can be determined from Descartes' rule of signs. So let f of x be a polynomial with real coefficients. The number of positive real zeros is either equal to the number of sign changes of f of x or is less than this number of sign changes by an even integer. The number of negative real zeros is either equal to the number of sign changes of f of negative x or is less than the number of sign changes by an even integer. So you'll see this in action. Determine the possible number of positive and negative real zeros of negative x to the fourth minus 3x cubed plus x squared minus 4x minus 12. So first, let's write f of negative x. So negative x to the fourth is still positive, so we're going to be left with negative x to the fourth. Basically, every odd power is going to change sign. So plus 3x cubed plus 6x squared plus 4x minus 12. So positive real zeros, number of, is the number of sign changes of f of x. So we have negative, negative is not a sign change, positive is a sign change, back to negative is a sign change, and then negative is not. So there are two sign changes. So it's either going to be 2 or less than 2 by an even integer. So 2 minus 2 is 0. And we can't go any lower than 0. So we have 2 or no positive real zeros. For the number of negative real zeros, we look at f of negative x. So negative to positive, that's a sign change. To positive is not, to positive is not, to negative is. So there are two sign changes here. So we have 2 or no negative real zeros. So now to find the real roots or the real zeros of a polynomial, we combine everything that we have learned so far. And we will do that for this polynomial. 4x cubed minus 3x minus 1. So the first thing we want to do is list out the possible rational zeros. And we do this using the rational zeros theorem. So it's going to be factors of 1 over factors of 4. So it'll be plus or minus 1 over 1, plus or minus 1 over 2, plus or minus 1 over 4. The second thing we want to do is determine how many of the real zeros could possibly be positive and how many could be negative. So number of real zeros, positive real zeros. Let's do positive zeros. Positive to negative is a sign change, negative isn't, so we have 1 or less than 1 by an even, but if you subtract 2, you get negative 1. That's not possible. So we know we're going to have exactly one positive real zero. Number of negative. So what I'll do is I'll write out f of negative x up here, and we'll get negative 4x cubed plus 3x minus 1. Typically, I will do this in my head. I won't write it out. So negative to positive is one sign change, back to negative is 2. So we have 2 or no negative real zeros. So now, the third step, the third thing we want to do is test these possible rational zeros. Well, I know that I'm going to have positive real zeros. I have to have 1. So all I'm going to do is test these positives. So start with 1. Then we have 4, no x squared, negative 3, negative 1. And against this very last term here that we care about, we want that to be 0. 4 times 1 is 4, plus 0 is 4, times 1 is 4, minus 3 is 1, times 1 is 1, minus 1 is 0. Perfect. 1 is a 0. So the fourth thing we're going to do now is write 4x cubed minus 3x minus 1 as x minus 1 by the factor theorem times 4x squared plus 4x plus 1. Now, the goal is to get to this point. So you would want to repeat these steps until you get to a quadratic, because now quadratics can easily be factored or easily be solved using the quadratic formula. This is a perfect square binomial. So we have x minus 1 times 2x plus 1 squared. Right, so remember from algebra, a plus b quantity squared was a squared plus 2ab plus b squared, and this is what we call a perfect square binomial. That's how I was able to determine this here. So the final thing we want to do is just list out our zeros. So we have 2 zeros. We have 1, and we have negative 1/2. Right, by the factor theorem again. Now, you may be saying, well, hold up. I thought we were supposed to have either 2 negative real zeros or no negative real zeros. Right, from right here. You only listed 1. Well, this is not a violation of Descartes' rule of signs, because this negative 1/2 actually has a multiplicity of 2. So it actually appears twice. However, we're only going to list it once. So we actually do have 2 negative real zeros. It just so happens that negative 1/2 occurs 2 times. Now, a polynomial need not only have real zeros, it can also have complex zeros. So let's suppose that we are given a polynomial f of x with real coefficients that has a plus bi as a 0. And remember, this I is defined in such a way that I squared is negative 1. So if that's the case, we can write f of x as x minus the quantity of a plus bi times q1 of x, where q1 of x is some polynomial. However, since f of x has real coefficients, we need a factor that quote-unquote cancels out this imaginary component. The only way to do this is to multiply by the complex conjugate. Thus, f of x would be x minus the quantity of x plus bi times x minus the quantity of a minus bi times q2 of x, where q2 is now some polynomial. So this leads us to the complex conjugate theorem, which states that if f of x is a polynomial with real coefficients, and a plus bi is a complex zero of f of x, then its complex conjugate, a minus bi, must also be a 0. And now we look at one of the most important theorems of all of algebra. It is called the fundamental theorem of algebra. And it states, let f of x be a polynomial of degree n greater than 0. Then f of x has at least one complex 0. A consequence of the fundamental theorem of algebra is called the linear factorization theorem. And it states, let f of x be a polynomial of degree n greater than 0, and let a be a non-zero real number. Then f of x has exactly n linear factors. That is, f of x can be written in the form a times x minus c1, a times x minus c1, times x minus c2, times x minus c3, so on and so forth, times x minus cn, where each of these ci's is a complex number. Now keep in mind that a real number is also complex, right? For example, if we look at the number 8, can't I write 8 as 8 plus 0i, making it complex? And any number can be written, any real number can be written as the number plus 0i. Hence, every real number is complex. So this linear factorization theorem can also be interpreted as a polynomial of degree n has exactly n zeros if we account for the multiplicities. So we're going to go ahead and find all the zeros of a polynomial, specifically of the polynomial 3x cubed plus 9x squared plus x plus 3. So really, we're going to be doing the exact same thing as we did for the real zeros. Except when we get down to that final step with the quadratic, we will include all the complex zeros as well. So the first thing we want to do is list out our possible rational zeros. So this is from the rational zeros theorem. So factors of 3 are 1 and 3, and look, this is also a 3. So we're going to have plus or minus 1 over 1, plus or minus 3 over 1, plus or minus 1 over 3, plus or minus 3 over 3. Now we want to determine the number of positive real zeros and the number of negative real zeros. So look, there's no sign change in f of x, so we're not going to have any positive real zeros. This is going to cut our work in half, which means rational zeros now, we take out all the positive cases. Now for the number of negative real zeros, we look at the sign changes of f of negative x. Again, I will rewrite this. This is something I typically do in my head, though. So it'll be negative 3x cubed plus 9x squared minus x plus 3. So we go negative to positive is a sign change, to negative is another sign change, back to positive another. That is 3 sign changes. But we could also have less and even. So subtract 2, we're left with 1. If we try to subtract 2 again, we get negative 1. So we have either 3 or 1 negative real zero. So since we have no positives, the first one I'm going to check is negative 1. Right? Again, no positive means ignore all these positives up here. So it'll be 3, 9, 1, 3. And this is the term we're interested in. That better be 0. Carry down the 3 times negative 1 is negative 3 plus 9 is 6 times negative 1 is negative 6 times 1 is negative 5 times negative 1 is 5. That's 8. Oh dear, that is not a 0. So negative 1 is not a 0. So that essentially means what I can do up here now is completely cross out plus minus 1. Now let's try negative 3. 3 times negative 3 is negative 9, plus 9 is 0, times negative 3 is 0, plus 1 is 1, times negative 3 is negative 3, plus 3 is 0. Oh, good. So this negative 3 is a 0. So we can write 3x cubed plus 9x squared plus x plus 3 as x plus 3 times 3x squared plus 1. We're at a quadratic, so we're done. So we have x equals negative 3 as a 0 already. This 3x squared plus 1 now. Well, if this 3x squared plus 1 is 0, then this says that x squared would equal negative a third. So these are our imaginary components. So our zeros, we have negative 3. Then we will have negative 1 over the square root of 3i and positive 1 over square root of 3i. And how I got those is just by solving this here by taking the square root. Now let's check. We should have exactly 3 zeros if we account for multiplicities. Well, all the multiplicities up here are 1. So we count 1, 2, 3. We have them all. We will now look at finding all of the zeros of negative 5x to the 4th minus 5x cubed plus 25x squared minus 5x plus 30. Now, in this case, let's simplify this. And let's write g of x is equal to negative 5 times x to the 4th. Or I'm sorry, I'm going to keep this as f of x. Negative 5 times x to the 4th plus x cubed minus 5x squared plus x minus 6. And this I'll call my function g of x. Well, if it's a 0 of g of x, it will be a 0 of f of x. So I'm going to apply all the steps on this g of x instead of f of x. This is just to make the arithmetic easier. So possible rational zeros. Factors of 6 are 1, 2, 3, and 6. Our leading is a 1. Perfect. So our possible zeros would be plus or minus 1, plus or minus 2, plus or minus 3, and finally, plus or minus 6. So now we want the number of positive real zeros. So we want the sign changes in g of x. So positive, positive, to negative is a sign change, back to positive is a sign change, back to negative is another sign change. So that's 3, or less than even. So 3 or 1. Number of negative real zeros. So we want g of negative x. This would stay positive. This would switch to negative. That would stay negative. This would switch to negative, and that stays negative. So we have only one sign change. All right, so I know I'm going to have exactly one negative real zero. So what I'm going to do is only test the negatives. All right, so let's try negative 1, and let's see what we get. So we'll have 1, 1, negative 5, 1, negative 6. And again, we want this last term to be 0. If I can actually draw it right, that would be wonderful. There we go. 1 times negative 1 is negative 1, plus 1 is 0, minus 5 is negative 5. times negative 1 is 5, plus 1 is 6, times negative 1 is negative 6. That's not going to work. So we know negative 1 can't be a 0. Alright, so let's try negative 2 instead. 1 times negative 2 is negative 2, plus 1 is negative 1, times negative 2 is positive 2, times negative 5 is negative 3, times negative 2 is 6, that's 7. This won't work. This is negative 14. Alright, let's try negative 3. Times 1 is negative 3, plus 1 is negative 2, times negative 3 is 6, plus negative 5 is 1, times negative 3 is negative 3, plus 1 is negative 2, times negative 3 is 6, and that's 0. Perfect. So negative 3 is a 0. So we're going to have x to the 4th plus x cubed minus 5x squared plus x minus 6 is equal to x plus 3 times x cubed minus 2x squared plus x minus 2. So now we want to reapply all of the steps we just did now on this function. So the possible rational zeros are going to be plus or minus 1 or plus or minus 2. However, we've already tested negative 1 and negative 2. They weren't zeros before, so there's no way they can be zeros now. Also, we know that we can only have one negative real zero, so we can also just eliminate that way. So now we're down to just 2 possible positive rationals. So we test each one. Well, first let's look at the sign changes, right? So number of positive real zeros. So there's a sign change, another sign change, another sign change. So we're still going to have 0 or 1, which we already knew, right? So for room, I'm going to erase that. So let's try 1. So we have what? 1, 2, 1, negative 2. All right, it is this final term here I care about. Bring down the 1. 1 times 1 is 1. Minus 2 is minus 1. Times 1 is minus 1. That's 0. That's 0. That's negative 2. That doesn't work. Which means it has to be positive 2. But we still need to know what we're left with. So 2, 0, 0, 1 times 2 is 2, negative 2. There we go. So I'm going to move on to the next slide. So what we've now done is we've now written x to the 4th plus x cubed minus 5x squared plus x minus 6. We had that x plus 3 there. And we've now found a factor of this is x minus 2. And we're left with x squared plus 1. We are now at a quadratic factor, so we stop there. Now, this says here that x squared plus 1 is equal to 0, so x squared is equal to minus 1. So the zeros, we have negative 3, positive 2. Now we have here x squared equals negative 1, means x is either negative I or positive I. Now the degree was x to the 4th. 1, 2, 3, 4. We have all 4 zeros. So the zeros are negative 3, 2, negative I, and positive I. Now obviously when trying to graph a function and you're trying to find the intercepts, we ignore the complex components, the complex zeros. We'd only be looking at these real zeros here. And so that concludes our study of how to find the roots of a polynomial function.